What's up, you guys? It's Smith Brothers. I thought I would take a second and walk you through word equations to chemical equations number 5. So we spent a decent amount of time with this last week, and essentially what we're doing is we are taking a word description of a chemical reaction, and we are building that into a skeleton equation. And if you remember, you guys, a skeleton equation is any type of chemical equation that we haven't taken the time to balance it and see if it adheres to the law of conservation of mass. So we're going to start by kind of walking through this. I'm going to give you some reminders. When we're done with each of these problems, I will also go through and let you know what type of a reaction it was. Remember, if we had those notes from a couple of weeks ago where we were using what's in the reaction to tell us what kind of reaction is it. Is it a decomposition or a synthesis or a double displacement or a single displacement? And I'll walk you through that as well, so we're kind of killing two birds with one stone here. So let's go through our process. And the first part of our process is we are simply going to read the problem out loud. Dissolved barium chloride reacts with dissolved potassium sulfate in water. Barium sulfate precipitate and aqueous potassium chloride are made. There's a lot of stuff going on there. So let's start with what we know as far as our reactants. So as far as the reactants, and if you remember in a chemical equation, reactants are anything that's on the left of the arrow and products are anything that's on the right. So we're going to start with our reactants. We have barium chloride reacts, that's another way of saying plus sign, with dissolved potassium sulfate. Now this all means something, you guys. Remember, if we're dealing with dissolved, there's something we have to do with that. So let's go ahead and just set up the left side of our equation. So we have barium chloride. Barium is Ba on the periodic table. Chloride is Cl on the periodic table. Reacts, so we're going to put a plus sign. Now, one of the things I want you to remember is that we're dealing with dissolved, which means that this is an aqueous solution of, and so I have my little abbreviation that's hard to tell, that's an AQ for aqueous, plus dissolved potassium sulfate. Now, potassium is the letter K on the periodic table, and if you remember, you have a periodic table with all kinds of information on it. And one of the things you have to remember is when we say potassium sulfate, you have to look for that suffix, ATE, because that suffix is a clue that sulfate is one of our polyatomic ions, and it's on our polyatomic ion list. And if we look here, we see that sulfate has a chemical formula of SO4, and it has this -2 right here, and we'll talk a little bit about what that means in just a second. So if we go back, we know that this is going to be KSO4 because that's the chemical symbol for sulfate, and we're going to go ahead and put that in parentheses. Okay? This is also dissolved, so this is also going to be an aqueous solution. We're going to note that. And then it tells us that it forms, so when forms is another way of saying this is where the arrow goes. It forms barium sulfate, so Ba, and remember sulfate over here, SO4, and now it says here that the barium sulfate is a precipitate, and that's a fancy way of saying a solid. Now, if you're not sure where I came up with that information, that means you're going to need to go to this document that you got last week, and you're going to go to number 7 in the document, because this part of the document, number 7, reminds you of some tricky things. And one of the things that reminds you is that precipitate is another way of saying that something is solid. Okay? And if we see the words dissolved in, it means something is aqueous. So that's how I remembered to put those correct symbols. So like this barium sulfate, which is a precipitate, this potassium sulfate was dissolved, this barium chloride was also dissolved. So we have, one more time, dissolved barium chloride reacts with potassium sulfate in water. Barium sulfate and aqueous potassium chloride are made. So that's going to be my barium sulfate precipitate plus aqueous potassium chloride, so KCl, and that's aqueous. So we're going to put that little symbol right there. Now, one of the things that we have to do next in our process is we have to determine if these compounds are held together by covalent bonds or ionic bonds, because that really does make a big difference in how you set this up, because what we're trying to do right now is figure out what subscripts we should have on all of these. Okay? So we know that based on what we figured out earlier. Now there's a bunch of information again in this little packet that I gave you last week. Okay? And one of the things that we have to remember is we have to remember the charges of the ions of all of the elements on the periodic table. So we have barium chloride. So let's find barium on the periodic table. Barium is right here. It's an alkaline earth metal, and all of the alkaline earth metals have a 2+ or a +2 charge of their ions. If it's in this first column, those are the alkaline metals, it's +1. If it's over here in group number 13, it's a +3, plus or -4, nitrogen -3, oxygen group -2, and then the halogens -1. Now, as far as getting that information, just a quick reminder, if you look at number 3 on this things to remember when you're writing out equations from word equations, there's a bunch of information right there that will remind you of exactly these things. As far as this group of elements from here, group numbers 3 through 12, that's the transition metals, and there's some information on the transition metals on the second page. That's what this table tells you, and we'll come back to that in just a few minutes. Okay, so what we're trying to figure out now is what subscript should go on these. And the first thing I have to remind myself is that barium chloride is ionic. And because it's ionic, I have to pay attention to the charge, because the overall electrical charge of this compound needs to be 0 because this is ionic. I know it's ionic because ionic compounds or ionic bonds are in place when we have a metal bonding with a nonmetal. Barium is one of the alkaline earth metals, which means it's a metal, and it's bonding with chlorine, which is a nonmetal. So we know this is ionic, which means that we need to have an overall electric charge of 0. Right now, barium has a charge of +2, and chlorine has a charge of -1 because it's a halogen. So right now, this compound is not electrically neutral, which means I'm going to need some more chlorine, which means that I'm going to go ahead and erase my little aqueous symbol here, and I'm going to put in the subscript of 2, because now what I have is I have 2 chlorines, each with a charge of -1, which means that the overall charge of chlorine now is -2. +2 plus -2 means that it has an overall charge of 0, so this is ready to go. This is now a correctly written ionic formula for barium chloride. Now I have to go through and check with my other compounds as well to see if they're ionic or covalent. Now if this had been covalent, I wouldn't necessarily need to go through this process, because covalent compounds were not as adherent to that because of the nature of what the electrons are doing. It's okay if covalent compounds are not electrically neutral because they're sharing those electrons, not giving and taking them. So that even charge is not as important. So let's look at potassium. Potassium is a metal. Now sulfate is a substance, you guys, but it is a non-metal substance. It's a combination of sulfur and oxygen, which are both non-metals. So sulfate is essentially a covalent compound. Fun fact, all of these polyatomic ions are in fact covalent. I know, crazy, right? So this is also ionic, which means that the overall charge of this has to be neutral as well. So right now, I have potassium, and if I look at my periodic table, or actually what I'm going to do is I'm going to go ahead and just look at this little hint right here. Potassium is an alkali metal, and if you remember from number 3 on our important document, all alkali metals have a charge of +1. Okay? Again, sulfate, you guys, is it's a polyatomic ion, which means it carries an overall charge. And if I look, the overall charge of sulfate is -2. So that is what I'm going to put right up here. And I can see that this compound is not electrically neutral, which means I'm going to have to put a subscript on here. And what I'm going to do is I'm going to put a subscript right here on potassium, because now I have 2 potassiums that are hanging out together. So this is a +1, that's a +1. And as a result of that, the overall charge of K2 is +2, and now this is electrically neutral. Now I have to do the same thing over here because these are both ionic compounds, same thing. Now this one's kind of nice because barium has an overall charge of +2. Sulfate has a charge of -2, so there's nothing I need to do to barium sulfate. I can just leave that one alone. I have to check with my calcium chloride, or I'm sorry, my potassium chloride. Potassium is +1, chlorine is -1, so I'm good here. This is a properly written skeleton equation for this word problem. Now, the next thing we want to figure out is what kind of reaction is this? Now, I can tell just by looking at this that this is what we call a double displacement. And sometimes you hear it called a double replacement reaction. And the reason it's a double replacement reaction is because we have essentially elements that are switching place during the reaction. Let me give you an example. So what I have is I have barium bonded with chloride or chlorine in this part of the equation. And then I have potassium bonded with sulfate in this part of the equation. When I have the reaction, what's happened is that the barium has switched places with the potassium, and now it's bonded with sulfate over here, so that's one displacement. The barium has displaced the potassium. In this one, what we have is originally the chlorine was bonded with barium, but after the reaction, what happened is that the potassium has displaced the barium and is now bonded with chlorine. So that means I've had two different things that have been displaced, both the barium and the potassium. So as a result of that, we identify that as a double displacement reaction. Now, just so you know, when it comes to identifying a double displacement reaction, if you see a compound and then a second compound on the reactant side and then two compounds on the product side, it's very likely you're dealing with a double displacement reaction. That's usually a dead giveaway. Now, if you're not entirely sure how to identify these, you can go to these notes right here, these doodle notes on chemical reactions. And if you look at numbers 3, 4, 5, 6, and 7, it goes through all the different kinds of reaction, and you can find those in the notes from last week. You'll have to look for them on Google Classroom, but you're looking for those chemical reaction doodle notes, and that's the best place to find information on these different reactions. But like I said, I'm going to talk you through it today as well. Okay, let's do the next one. Now I'm going to go a little faster this time because I don't want you to have to watch this video all day. All right, so calcium chloride, which is a solid, and I just know that because chlorides like this tend to be salts, which are solid, and potassium phosphate are dissolved in water, and they react to form aqueous potassium chloride and calcium phosphate powder. Powder, you guys, is another way of saying solid. So one of the things you have to get used to, and this just takes time and practice, is knowing what all of these things mean. They all mean something. So let's do calcium chloride first. CaCl plus potassium phosphate. Now there's that ATE suffix again, you guys, which means I'm going to go ahead and go to my periodic table. Here's my periodic table. I'm going to flip it over. Because it's an ATE suffix, I know I'm dealing with one of these polyatomic ions. I'm going to go down here because they are in kind of alphabetical order. And look, there's my phosphate right there. It's PO4. So calcium phosphate, so KPO4, and I'm going to put that in parentheses, dissolves. Now, potassium phosphate is also a solid, so I'm going to go ahead and note that these are both solids. They react, which is another way of saying, time for the arrow, aqueous potassium chloride, so KCl, that is aqueous, and remember, and is another way of saying, that's where I put my plus sign, calcium phosphate, Ca, and remember from over here, phosphate is PO4, and we're going to throw some parentheses around it, and this is a powder, so we know it's solid. Now again, the next thing we have to do is we have to decide if these compounds are ionic or covalent. Well, I can tell you right now these are all ionic. Calcium is a metal, chlorine is a nonmetal. Potassium is a metal, phosphate is a nonmetal. Potassium is a metal, chlorine is a nonmetal, so I know I'm dealing with all ionics, so I have to get my subscripts right to show that all of these are chemically neutral. So let's go ahead and let's do our charges. Now, calcium is an alkaline earth metal. There it is right there. And that is a dead giveaway that that's a 2 plus or plus 2. So plus 2. Chlorine is a halogen. And if you remember, all of our halogens are -1. So currently, this is not chemically neutral, which means we've got to do some subscript work. And so we're going to put 2 down here, because again, that's going to make this chemically neutral, giving this an overall charge of 0. Now, potassium is a -1, and if we look at phosphate here, if you recall, phosphate is a -3. So that means, again, I've got to do some work here, and specifically what I'm going to do is I'm going to go ahead and make this potassium K3. So if I look to the other side, this is, and we just did this up here, so we know that this one is fine just the way it is, because that's a +1 and that's a -1. Potassium chloride is chemically neutral. And this is a +2 and a -3, which is awkward, because now what we have to do is we have to put subscripts on these to help this work out a little bit better. And again, this whole thing is -3, and this calcium is a +2. So this is where we have to go all the way back to like elementary school math with common denominators. What is a number that if I multiply that 2 and 3 have in common, and that number is 6? Okay? So if I want these charges to work out, it means that their overall charge of this still has to be 0. Now, if I make this calcium, if I put a subscript of 3 down here, and this phosphate, if I put a 2 out here, let me show you what happens. By doing that, I take 3 times +2, and that's going to equal +6. If I take 2 times -3, I'm going to end up with a -6. And now this is chemically neutral as long as I have 2 phosphates getting together with 3 calcium atoms. So like I said, now you'll get used to when you see these -2 +3, you'll know automatically that you're going to be dealing with something that's going to give you a total of 6. And that's just, you just get really good at identifying that. Okay? Next up, I'm going to grab a quick sip of water here. Throat's a little dry from all this talking. All right, next one, sucrose, which is another, sucrose is a fancy way of saying table sugar. So, yay, sucrose. Sucrose, which is C12H22O11, burns, which is another way of saying, I'm going to put my plus sign there, in oxygen. Now, this is always going to be oxygen gas. And remember, you guys, oxygen is a diatomic, okay? And if it's, and this goes back to your notes, if it's a diatomic, it means it's always going to exist as O2, as long as it's all by itself. Okay, oh, I forgot to tell you something. I forgot to tell you what kind of reaction this is. Well, based on what we previously did, if you recall, I said that if you've got a compound here and a compound here on the reaction side, and then a compound here and a compound here on the product side, again, we are dealing with another double displacement reaction. And again, I can't stress this enough. Go to your notes. But again, if I have, and again, you guys, where I see the displacement is on this side, I have calcium pairing with chlorine. On this side, the calcium gets displaced by the potassium. On this side, I have potassium pairing up with this phosphate. Over here, the calcium, or the potassium has been displaced by the calcium, so I have 2 different displacements. So this is a double displacement reaction. So if we go back here, I've got sugar, burns in oxygen, and then carbon dioxide, water, and heat are produced. So produced is another way of saying I've had a reaction, so I have to put my arrow there, and I have carbon dioxide, and based on what I know from Unit 4, I know that if it's a dioxide, it means I have 2 oxygens, plus water, which is H2O, plus heat. I'm not going to worry about putting heat in the equation, but if I did, I would just put plus heat. Okay. Now let's talk this is sucrose. This is sugar, you guys. So I know sugar is going to be in solid form. Burns in oxygen, gas. Carbon dioxide exists at room temperature as a gas. And usually my water, when it's done, is going to end up as liquid water and then heat. So now I have to determine if all of this works okay as far as what's in it. And the short answer is yes, and here's why. I'm not dealing with any ionic compounds here. Sugar is a covalent compound. O2 is a covalent compound, covalent, and because of that, I don't have to worry about whether my compounds are electrically neutral. So this is all I have to do for this one. I'm done. Yay! Okay, let's go to number 4. Aqueous calcium hydroxide reacts with, so that's one of my reactions, reacts, which is another way of saying plus sign, sulfuric acid, and they do give you the formula, but I will show you where on your periodic table you can find the sulfuric acids. A precipitate, there's that word again, which is another way of saying solid, precipitate of calcium sulfate, and water and heat are formed. So let's go ahead and write out the reactant side first. Calcium hydroxide, so Ca. Now, hydroxide, sometimes you guys, those polyatomic ions don't end in ATE. They end in IDE, like hydroxide, which is OH. So calcium hydroxide, OH, plus, and that says aqueous, we know that's going to be an AQ, plus, or reacts with, I can give myself a little bit more room here, can't I? I don't have to be so squeezed in. Aqueous plus sulfuric acid, which is H2SO4. Now, if you're not sure where to find the chemical formula for sulfuric acids, you should look in this part of your periodic table, because you'll see sulfuric acid right there, and there it is, H2SO4. So sulfuric acid, then I have my reaction. I end up with calcium sulfate, so Sa, there's that ATE. So that tells me that that's going to be a polyatomic ion. There it is, sulfate, with a formula of SO4, calcium sulfate, SO4. And I'm going to put that in parentheses because that's a polyatomic ion. Now notice, you guys, I didn't put this in parentheses because that in itself, you guys, is not listed as a polyatomic ion. You can see the way sulfuric acid is written there. That's a little bit different than what we're dealing with right here. Okay, so calcium sulfate plus water, and then if I wanted to, I could put heat out here because that's formed as well in the reaction. Oh, I forgot to tell you what this reaction was. I'll tell you in a minute. We'll do this one first. Okay. Now, the first thing I have to do is I have to figure out, do I have any ionic compounds? Well, calcium is a metal. It's an alkaline earth metal. Hydroxide is a polyatomic ion, so we know that this is non-metal, so we know that this is ionic. So I'm going to go ahead and it's an alkaline earth metal, so it has a 2+ charge. Hydroxide, according to this, hydroxide, there it is. Oops, you can't see that, is a -1. So what I notice right away is that right now this ionic compound is not electrically neutral, which means I'm going to have to put a subscript down here so that I have 2 hydroxides, which now gives me a -2, which now causes this to be electrically neutral. Huzzah. On the other hand, this compound, sulfuric acid, you guys, this is all nonmetals. Hydrogen, sulfur, and oxygen. This one is not ionic, so I don't have to worry to take the time to figure out if it's electrically neutral. On the other side, we have calcium sulfate. Calcium we've already determined is a metal. This is a polyatomic ion, so we know it's a nonmetal. This one is a +2, I got to go figure out what my charge of sulfate is. It's a -2. So there's nothing I need to do because these are already together and neutral. And water is, again, not ionic because hydrogen and oxygen are both nonmetals, so I can leave that one alone. So now that I have that one set up, I have that equation set up properly as well. Now let's go back and determine what kind of reactions these are. Now, if you look in these notes, one of the things that it talks about on the very last page is something called a combustion reaction. And combustion reactions, you guys, are any fuel plus oxygen gas, and when it's done, you're going to get water and carbon dioxide. So if you take a close look at what we have with 3, we have sugar, which is our fuel, burning with oxygen, oxygen gas, and the products that I end up with are carbon dioxide and water. This is a classic combustion reaction. And it is because the definition of any combustion reaction is any fuel reacts with oxygen gas, and it ends up forming carbon dioxide and water. If it has those ingredients, it's automatically a combustion reaction. Okay, so just keep that in mind. This one also happens to be a displacement reaction, but more importantly, it's a combustion reaction. Okay? All right. Next up, let's do this last one. We have sodium metal. Now, when you see the word metal, you guys, that's another hint. That's a solid. Oops, I forgot to do these up here. Precipitate, that's a solid. And water, that's going to be liquid water. There we go. Sodium metal reacts with iron. Now, that's important. Iron 3 chloride, iron metal, and sodium chloride are formed. All right, so I have sodium metal. So that's going to be Na, and that's a solid because it's a metal. Reacts, so that's another way of saying that's where my plus sign goes, with iron 3 chloride. So I'm going to put FeCl. Now, I don't have to put the 3 in my equation here, but just know that this is significant, and we'll talk about why in just a second. So it reacts with iron, and iron metal and sodium chloride are formed. So iron metal, Fe, and sodium chloride, NaCl, are formed. So we have a single element right here, so I don't have to worry about subscripts here because this is all by itself. This is not a diatomic, so I'm not going to have a subscript on this sodium. Now, on the other hand, what we have here is we have iron and we have chlorine. Now, this is iron 3, and if we go back to our document that we got the other day, the things that we should know about writing skeleton equations and word equations, if we go to the second page, we have a whole list of transition metals. Now, the transition metals on the periodic table, and I talked about this a little earlier, are these columns or these groups, group 3 through group 12. And they have lots of different versions of themselves, lots of different ions of themselves. Now, if you see something like iron 3, look, here it is right here, that little Roman numeral 3, that means that what it has a charge of +3. So like I said, the Roman numeral is significant because look, I have iron 2 right here, and iron 2 has a charge of 2+ or +2. So that becomes significant because what we know is that this is an ionic compound right here, which means this compound needs to be chemically neutral. Iron 3 has a charge of 3+ or +3. Chlorine, because it's a halogen, is over here in this column where everything is a -1. So if I want this compound to be electrically neutral, it means I have to have 3 chlorines. So that's what it's going to be, an FeCl3. Now, once we have the reaction, chlorine gets, or the iron is free, and we have the sodium bonding with the chlorine. This is absolutely ionic. Sodium is a metal, chlorine is a nonmetal. So we have to go through and we have to figure out the charges. So because this is an alkali metal, it's in that very first column, which makes this a +1. Chlorine is a halogen, which makes it a -1. So there's nothing we need to do to this sodium chloride. We are good to go. Now the only thing we want to do is make sure we have all of our states of matter. So sodium metal reacts with iron chloride. It's a chloride, which means it's going to be a solid. Iron metal, which then is a solid. And sodium chloride. Table salt, think of that. Table salt is a solid when you sprinkle it on your French fries. French fries. All right, anyway. So with that said, you guys, as far as what kind of reaction this is, well, again, you guys, we're dealing with a displacement reaction. But this time, only one thing is getting replaced. So here we have a compound that is FeCl. After the reaction, right now the iron is pairing with the chlorine. After the reaction, we see it's the sodium pairing with the chlorine. So the iron got booted out. It got displaced by the sodium. So we have one thing being displaced. So this is a single displacement reaction. And like I said before, you really do need to look at those notes, these doodle notes, because it takes you through how to identify the other types of reactions. And the other types of reactions are synthesis reactions, decomposition reactions, single displacement, double displacement, and combustion. Okay, so look at those notes, and it is very helpful when it comes to how you're going to identify the different types of reactions. All right, so if you have any questions, let me know, but that is the solutions and the thinking for Practice 5, which is word equations to chemical equations.